There are a number of factors that can affect the power of a hypothesis test. And remember, whenever we're talking about power, we're talking about the alternative hypothesis being true. Power is necessarily undefined if there isn't a real effect. There's no way to correctly reject a false null hypothesis if the null hypothesis is true. So these are factors that affect that red distribution and where it is in relation to the blue distribution. To start, perhaps the most intuitive factor that affects power is the size of the effect. We saw this before when I was talking about coin flips. It's a lot easier to detect a biased coin if the bias is huge, such as 10 heads out of 10 would be reasonable to happen by chance, versus bias that's incredibly small, bias of one coin flip in a million. So the size of the effect will change our power, and we want our power to be as large as possible, so we want to maximize the size of an effect. Now looking at this in formulas, we can see that the size of the effect is really the numerator of our z sub x bar. In fact, our x bar minus mu sub x bar there is actually estimating the mean under the alternative hypothesis minus the mean under the null hypothesis. Remember, if we're in a situation where we're talking about power, then our sample mean is coming from that population under the alternative hypothesis. So our x bar is estimating mu alternative. Now, as for mu sub x bar, notice that we found that value assuming the null hypothesis is true. That is, what means we would likely get if there was no effect. So, mu sub x bar is really an estimate of the mean under the null hypothesis. So all of this is to say that as we find more separation between the mean under the alternative hypothesis and mean under the null hypothesis, the numerator of our z sub x bar, our test statistic, will tend to be larger. Anything that makes those larger on average will tend to increase our power. Now going back to our diagram, we can see this effect on power by simply increasing the effect size, which is akin to saying I'm going to shift the distribution. Now we're talking about an effect size of 40 IQ points. If on average we were to increase people's IQ by 40 points, we've substantially reduced our miss rates. Notice why this is. Power is still the 1 minus beta region there, and the beta region is the tiny tail here of the sampling distribution under the alternative hypothesis where we were unlikely enough and unlucky enough to get a sample mean that wouldn't allow us to reject the null. Notice that will happen. There will be times, even with a huge effect, that sampling error worked against you. You happened to get a sample mean that was so low, it was easily attributable to chance. Because remember, the reason we're doing this is to decide whether our sample mean, the one we get from an experiment, is reasonably attributable to chance or not. And there will be times, even with large effects, that we'll get a sample mean that isn't far enough from that mean under the null hypothesis to allow us to reject the null hypothesis in totality as a reasonable explanation for the effect. So, even with large effect sizes, we'll still miss some of the time. But I hope you can see, compared to the previous situation with a smaller effect, we are missing much less of the time. Said differently, the power to detect a large effect is larger. Another factor that affects power, but perhaps less obviously, is the variability in the population. Now we can see this more clearly through the formula that we use. That is, the denominator of our test statistic is sigma sub x bar, the standard error of these sampling distributions. And sigma sub x bar is built out of the population standard deviation divided by the square root of the sample size. Now, all this means is if the population started out as less variable, that is, individuals in the populations had less variability in their IQs, we would expect to get sample means closer to the population mean. We saw this when we looked at sampling distributions. A sample coming from a population that has very low variability will tend to have a mean very close to the population mean. Now, we're not looking at the populations themselves right now, but the sampling distributions under two conditions, when the population mean was centered at 100 and when the population mean was centered at 120. So we're looking at the behavior of the sample means. But if the population was less variable, that is, people's IQs clustered much closer to the population mean, then these sampling distributions would have less variability as well. Now I'm going to change this and pay attention to what happens if we expect our sample means to be closer to their population means. Each of these sampling distributions will be drawn in. Now notice why this is the case. If under the null hypothesis, the sampling distribution was drawn in, we would expect more of our sample means to be close to 100. It would just be harder, if there's less variability in the population, for us to get a sample mean far from 100. Now, in the other state of the world, if our samples are coming from a population centered at 120, and that population also had less variability, then we would expect most of our sample means to be closer to 120. So notice what changed. I'll go back to the original circumstance, and when I go to the next one, notice what happens to the beta and 1 minus beta regions. When we have populations that are less variable, and so sampling distributions that are less variable, there are simply more samples coming from that population centered at 120, that sampling distribution centered at 120, that will exceed the critical value. Another way of saying this is, if our populations are not variable at all, then every sample mean will be right on top of its population mean. So there would never be a time where we would confuse a sample mean as simply a chance occurrence. That is, if we're drawing from a population where the alternative is true, and we're likely to get sample means right around 120, it would be incredibly hard to confuse one of those samples as coming from the blue distribution. Now it turns out, and you may have seen this already in the formula, that in addition to the variability in the populations affecting power, our sample size will also affect power. Now this again works through the denominator of our test statistic in that standard error, but instead of changing sigma, we can simply change the sample size and have the same consequence on those sampling distributions. That is, here's our original circumstance, but if we were to increase our sample size considerably, we would also draw in the sampling distributions. Now this is probably the main way that we will be able to increase power. It's very difficult to reduce the variability of a population. We'll actually talk about some ways we can, usually through better measurement systems, but we can always take more individuals into our sample. Remember, with incredibly large sample sizes, we're expecting our sample mean to be right next to the population mean. That's just the consistency of a statistic. As we put more individuals into a sample, the sample mean is likely to be closer to the population mean. So with infinitely sized samples, or even samples that are very, very large, we would expect our sample means to be right next to their true mean. And if our sample is coming from that red distribution, and we have an incredibly large sample size, our sample mean will be right next to 120. It would be very hard to get a sample mean with a very large sample size that could be confused as a sampling error only occurrence.